on to 2, 1, 3 avoiding linear extensions of a 0, 3 numbered poset. So again, here's our data that we were working with that we generated. So if you want to take a minute and see if you notice any patterns.
Powers.
Yeah, yeah.
Like moving across.
Sure, yes, yep. Yeah, so. And
Cube,
yeah.
cubes, fourths.
Yep. So all of those are covered in our theorem. So the number of linear extensions that avoid 2, 1, 3 in a 0, 3 numbered poset is, for an n by n poset, is n to the m minus 1. So why is that? So first we're going to claim that a linear extension of a 0, 3 labeled n by n poset avoids 2, 1, 3 if and only if all elements of a given n row are selected before more than one element in n rows above it are selected. So first, let's prove that if we select more than one element in rows above a given n row, we're going before we finish that n row, we're going to hit a 2, 1, 3. So suppose we've started this n row, suppose we've selected the 12 and the 11, and we have yet to select the 10. And we go up here and we select the 9. We could select any element, but we would have to go through the 9, so let's start there. And we pick another element. Notice that all elements above this n row, above the 9, are less than 9. And so that's going to act as our, so if we choose the 6, we're going to get a 2, 1. And we said that we didn't finish this n row, so we're going to have to come back to it at some point, and we're going to get a 2, 1, 3. So now for the converse, suppose that we have a pattern 2, 1, 3, and our 3 is in some n row. So let's say it's the 11 here. We're trying to show that the 2, 1 must come from n rows above this n row. So we're going to show that the 2, 1 has to come from up here. So if this is our 3, then our 2, 1 can't come from above it because we can't select those elements before we've set the 11. So those are out of the picture. Any elements below the 11 in this n row or in potential n rows below it are going to be greater than 11, so can't act as our 2, 1. Therefore, our 2, 1 is going to have to come from n rows above it. So, now that we have that, we can think about how we can add rows to our poset and how that affects the number of linear extensions we have. So, and try to prove our conjecture that way. So our conjecture tells us that we want to find n linear extensions of an m plus 1 by n poset for every one linear extension of an m by n poset. So imagine that this here is our m by n poset, and we're trying to add this row. We can also think about this as taking a linear extension of this m by n poset and trying to insert these elements into those linear extensions. So suppose we have that linear extension. We know that this 12 is going to have to be inserted at the very beginning because when we have this, this 12 is going to have to go first. So now we have to think about where we're going to put the 11 and the 10. So by our previous theorem, we know that the 11 and the 10 either have to come before the 9 or after it or some combination. So to illustrate that, we have this here. So the 11 and the 10 can either come before the 9, the 10 can come after the 9, or the 11 and the 10 can come after the 9. You can also think about this as placing the 9 amongst the 11 and 10, and there are 3 ways to do that in this case with our 4 by 3 poset, and in general there are n ways to do that. So that shows that for an n by n poset, we have, for a linear extension of an n by n poset, we have n linear extensions of an m plus 1 by n poset, which proves our theorem. So now we're going to move on to 1, 2, 3 avoiding linear extensions of a 0, 3 labeled n by n poset. So again, any observations? Well, we have the 1s, right? And we also have the Catalans that Ruth was talking about. So anything else beyond that anyone notices? So we didn't notice anything either. This is actually an open problem that maybe we'll work on next term, but if you have any ideas, let us know. But yeah, so now we're going to move on to patterns of length 4.